Hello everyone. In this video I'll be talking with you about the voltage of a capacitor. I'll be deriving that expression in this video. And so to start with, what exactly is a capacitor? Well, a capacitor is two plates separated by a dielectric. The dielectric is an insulative material that is in between those two plates. And so mathematically, capacitance C is defined as dq dV. That is to say, a change in voltage across the capacitor plates will have a change in charge distribution across those plates as well. And mathematically, that's what constitutes a capacitance. So the geometric factors, the material factors of a capacitor is that the area A divided by the distance D times epsilon will give you the capacitance. So these are physical factors that determine the capacitance. And what is area? Well, area is in reference to the plate area, but more specifically, it's in reference to the area of overlap between those plates. So in fact, you could make a variable capacitor by varying the overlap of those plates with respect to each other. If you vary the overlap, you can vary the capacitance of it, and that's how some really early variable capacitors were made. Next is D. Well, what is D? D is the distance here between the two plates. So the closer the plates are together is the more capacitance that you have, but of course you don't want the plates of the capacitor to be so close that you actually get voltage arcs and you defeat the functionality of the capacitor. So that's what D is, the distance between the two plates. Next we have epsilon. Now epsilon is the effective permittivity constant that you'll put here, but it's made up of the relative permittivity and the permittivity of free space. The relative permittivity is correlated to the type of material that you use here as your dielectric, such as paper or wood or some other insulative material, maybe styrofoam, plastic, even air itself. All of that has relative permittivity, and you'll look that up in the back of a textbook, probably in the appendix. You'll find different measures of relative permittivity for different materials. The permittivity of free space is a constant, it's a universal constant, and so that's how you get this constant of epsilon that you will apply here. So next, what we'll go ahead and begin to do is we'll take our empirical equation here, which says that IC of t times C dVc of t dt gives you a current. So that's empirical because you could go into a lab and you could see that if you apply a DC voltage to a capacitor and you have an amp meter to measure the current, the current reading will be 0. So that holds true because if we differentiate a constant with respect to time or any differentiation variable, then we'll get 0. So that holds true. Next, if we were to say use, instead of a constant voltage VDC, we use a sinusoidal voltage sine of omega t, which is time variable, it varies in time. With the time varying voltage, what we will see is that we'll notice with our amp meter, say we had this set up here with an amp meter, we would notice that the amp meter would register some current. And to be more specific about this type of current, what we'll do is we'll take notice of the fact that there's two different types of current. There is displacement current, and then there's conduction current. The type of current that we are talking about when we mention IC of t here is that we are talking about the displacement current. To the amp meter, it's indistinguishable. it looks like a regular conduction current, which is what you would have if you have a normal regular setup here. You have your amp meter, you have a resistive element. This is a capacitive element. This is a conduction current. This is a displacement current. And the difference between those two is that for the conduction current, electrons actually go through your resistive element here because it's actually being conducted through. With the displacement current, that's due to the momentary redistribution of charges from one plate to the other. It gives the effect of having a current go through the capacitor, but it doesn't. It only migrates. What the amp meter picks up is the momentary migration from one plate to another, and then back from that plate to another whenever this sinusoidal sine wave switches polarity. And so you have a migration going back and forth, and so you have what you call a displacement current because those charges are being displaced. So again, to summarize it, charges don't go through a capacitor, they go to a capacitor. In specific, they go to a capacitor's plates, to and from the capacitor's plates, but they do not go through the inside of the capacitor where you have a separation between the plates, where you have that dielectric. They don't go through that. They go to and from the plates, and so you have a displacement current. So that is what this IC of T is. It's a displacement current. And so we'll use this expression in order to get our voltage of our capacitor. So for starters, I'll restate that over here. And so we have IC of T equals C dVc of T dt. Next, what we'll do is bring 1 over C to this side. We'll divide out both sides by C, and we have 1 over C IC of T equals dVc of T dt. We'll bring over dt to the left-hand side, and so now we have 1 over C IC of T dt equals dVc of T. Just as an extra note, up here at this step, this is called an ordinary differential equation, and it's of first order. So mathematically, what you would find is that usually when you evaluate ordinary differential equations of the first order, what you do is you try to apply a technique of separation of variables so that you can therefore use integration techniques in order to recover the function that you're after. In our case, it's Vc of T. So now what we'll go ahead and do is we'll apply those integration techniques. And so now we have 1 over C, we'll do an integral here, IC of T dt equals integral dVc of T. Next, we'll establish some integration limits. We want to recover Vc of T, so we'll make that an integration limit. And so what that means is that we're going to need a integration variable substitution. So what I'll use is, you can use any variable. I'll make Vc of T equal to beta. And over here we have dt. Our integration variable is T, so we'll make a substitution for that and make T equal to alpha. Now next, we can go ahead and set up the integration. And our upper limit will be T, our lower limit will be T sub 0. And now we have IC of alpha d alpha equals integration with upper limit of Vc of T and Vc of T sub 0. And then instead of having dVc of T, we have d beta. And so we'll go ahead and carry on with that. I'll go ahead and make some more room over here. And bring that up over here. And so now we have 1 over C between T and T sub 0. We'll keep the left-hand side as it is generalized because for different situations, we will want to substitute in IC of alpha for whatever it is we are doing in our circuit analysis, whatever signal we have here. So we'll keep that generalized. And so we still have IC of alpha, d alpha, equals, and then over on this side we have beta to the first power over 1. That's evaluated between the limits of Vc of t and Vc of t sub 0. Then, when we go ahead and we evaluate further, we have IC of alpha d alpha equals Vc of t minus Vc of t sub 0. We have that, and we'll bring Vc of t sub 0 over to the other side, and then finally that gives us 1 over c between t sub 0, IC of alpha d alpha plus Vc of t sub 0 equals Vc of t. So this is the expression that we will find in textbooks for our voltage of our capacitor with respect to time. So that pretty much does it for this derivation. Thank you for watching this video. Hopefully it was helpful, and have a nice day.